Welcome to qnawire.
Hi, so for this problem we have the following reaction. We have copper 2 plus that is going to react in aqueous media with 4 equivalents of ammonia, same thing in aqueous media, to generate the coordination complex copper NH3 4 2 plus. Same thing in aqueous media. And the information that we're given is we know that the formation constant for this coordination compound is 4.8 times 10 to the 12, right? So the first thing that we need to do is to find out which one is going to be the limiting reagent. Just from the information that we have here, you can clearly see that the limiting reagent is going to be the copper sulfate, right? Because from this, we are mixing 16 milliliters of a 1.3 molar solution. So this corresponds to an amount of mole of, and this is the amount of mole for copper 2 plus because this salt is just going to dissociate completely in water, of 16 times 10 to the minus 3 liters. This is the volume that we have times the concentration, 1.3. In this case, the amount of mole that we are going to have of copper 2 plus, it is going to be 2.08 times 10 to the minus 3, correct? Now, the amount of mole that we are going to have of ammonia, it is going to be the same formula, but in this case, we are adding 1.4 liters of a 0.39 molar solution. So the amount of mole of ammonia that we're going to end up with, of course, it is going to be much larger than the original one. And we can verify using the stoichiometric relationship that if we divide this result by 4, this is mole of NH3. If we want to know if this is the limiting reagent, we know that 4 mole of NH3 is going to react with 1 mole of copper 2 plus. This means that the maximum amount of substance of copper 2 plus that this can react with is 0.135 mole. 1365 mole, right? So, of course, this quantity is much larger than the initial quantity of copper 2 plus that we have in solution. So, we know that the limiting reagent is copper 2 plus, right? So, this is going to be my limiting reagent. Now I can go ahead and proceed with my ice table. We know that of copper 2 plus, here I'm going to do the ice table in mole, and then we're going to get the concentrations to put into the equilibrium constant, just to make things a little bit easier for our final result. You can alternatively get all of the results directly in concentrations, but both procedures are equivalent, so do not worry too much about it in this case. So the initial quantity of copper 2 plus that we have is 2.08 times 10 to the minus 3. The initial amount of mole that we have of NH3 is 0.546. And let's assume that we're going to have 0 of this. The amount of change in mole that we're going to have, let's call it X. In this case, this would be minus 4X. And in this case, it would be plus X. That is the amount of copper 2 plus that is going to react. Of course, this quantity is going to be close to the initial value for concentration. But here we are not assuming anything yet. So that means that at equilibrium in amount of mole, we're going to get 2.08 times 10 to the minus 3 minus X, 0.546 mole minus 4X, and in this case, we're going to get directly the value for X. Now, we could convert this and do another X table for concentrations, just to exemplify how things are going to work out in molarity, the initial concentration, it is going to be the amount of mole divided by the total volume. In this case, the total volume, it is going to be the 16 milliliters that we had of the initial solution and the 1.4 liters that we have of the second one, right? So 16 times 10 to the minus 3 plus 1.4 liters. The total volume of our solution is 1.416 liters. That means that my initial concentration of copper 2 plus is 1.47. Let's write that 1.469 times 10 to the minus 3 molar of NH3. We're going to have 0.546 divided by 1.416 by the total volume. Here we're going to have 0.3856 molar. And here we're going to have still 0. The amount of change is going to be the same. This is going to be minus x, and this x it is going to be in concentrations now. And here minus 4x and plus x. And at equilibrium, we're going to get 1.469 times 10 to the minus 3 minus x, 0.3856 minus 4x, and x at the very end. So now what we need to do is plug everything into our equilibrium constant. So the formation constant for this compound, it is going to read concentration of the complex copper NH3 4 2 plus divided by concentration of copper 2 plus times the concentration of NH3 elevated to the fourth, right? Because we have that the reaction has this stoichiometric coefficient. So next up, we're going to replace the values that we found from these concentrations at equilibrium. So we're going to have x divided by 1.469 times 10 to the minus 3 minus x times 0.3856 minus 4x elevated to the fourth. So now we're going to make an approximation to make this equation a little bit easier. What are we going to base this approximation with? We're going to consider that the maximum amount of matter that can react would be 1.469 times 10 to the minus 3, right? This would be the maximum. If we multiply that value by 4, we would get 5.8 times 10 to the minus 3. If we compare that to this number, realize that that is going to change only to this decimal point, right? And that would be the maximum amount that we could get. So we're going to assume that 0.3856 minus 4x, it's going to be close to 0.3856, right? And this is going to be true if the result for 4x is lower or equal than 5% of my concentration that I'm approximating. If this condition is not true, then I need to solve the full equation. We need to solve the full equation for x. By now, we're going to consider that that approximation is true because we know that the equilibrium constant, it is quite high, is 4.8 times 10 to the 12. This is going to be equal to x divided by 1.469 times 10 to the minus 3 minus x. And Here we're going to introduce our approximation. The 4x is going to disappear and we're going to end up with this result. Simplifying this equation a little bit, we can get after evaluating these two terms, this one and this one, and multiplying one by the other, we get 1.0612 times 10 to the 11. This is going to be equal to x divided by this small number, 469 times 10 to the minus 3 minus x. Now we simply need to do the algebra. For solving for x, we pass the denominator to the other side multiplying, so we have times 10 to the minus 3 times 1.0612 times 10 to the 11 minus 1.0612 times 10 to the 11 times x. And this is going to be equal to x, right? This is simply 1.56, well, yeah, 1.56 times 10. This is 1.56 times 10 to the 8, and this is going to be equal to x times 1 plus 1.0612 times 10 to the 11. But we already know that 1 plus this very large number is essentially this number, so this is times 1.0612 times 10 to the 11 times x. Oop, sorry. So this means that x, it is going to be equal to 1.469 times 10 to the minus 3 molar. Or rounding this up to 1.47 times 10 to the minus 3. Let's recall that this value for concentration is equal to the concentration of NH3, 4.2 plus. And now to get the values of the concentration of copper 2 plus, what we can do is check up our initial equation. The initial value is actually super close to my final value, right? So what is the concentration of copper 2 plus? It is going to be a super small number. So since we made a lot of approximations along the way, what we can do is employ the concentration of NH3 that we're going to get. Recall that the concentration of NH3 was 0.3856 minus 4x, right? So 0.3856 molar minus 4 times 1.47 times 10 to the minus 3. Let's run out. Let's do the full result just for sake of precision, and then we're going to round things up. So 0.3856 minus 4 times 1.469 times 10 to the minus 3. We're going to have this concentration is 0.379, 724 molar. This is going to be our final concentration for this compound. Now we can solve for the concentration of copper 2 plus because we know that the formation constant times the concentration of NH3 divided by the concentration of my complex compound, copper NH3 4 to plus is going to be equal to the concentration of copper 2 plus. So this is, of course, this concentration times 10 to the minus 1, right? So 1 over concentration of copper 2 plus. So the number over here is 1.24 times 10 to the 13. That means that the concentration of copper 2 plus, it is going to be, let me just quickly check up the result, 4.8 times 10 to the 12 divided by 0.0147 times 0.379 or 378, sorry, 0.379 divided by, sorry, here, this is times 10 to the 14. So the concentration is going to be, at the very end, 8.06 times 10 to the minus 15 molar. And these are all of the concentrations that we were required to do. So the only difference that I see in between this result and your solution is the rounding up of the concentration of NH3, right, on your final answer. Because this value is the same that you find, and the concentrations of NH3 is the only one that changes up a little bit. And that would be all. Thank you.